Okay, I guess. So we started on the lecture. Okay, so let's start. So first, a couple of reminders that I mean that the change I said about the lunch, that is applicable today. So please have your lunch here. It is the same food as the mess. You won't miss anything. And the other thing is that you should get an email from us about the attendance statistic. So take a look at that, and then it's up to you to decide. So everybody will be getting their own. And yes, so you should, some people, I don't know if those people are here. So, so this might be just preaching to the already converted, but there are people who are seriously lacking in attendance. And yeah, you need to take care of, you need to either give me a very good reason why that is happening, as well as take care of what you're going to do in the next few days. Okay. So now, today what we'll be talking about is we'll be stepping back a little from the kind of things that Udit was talking about. Let's say, I mean, say the kind of work that he showed. Right, you can understand that how important characterizing uncertainty is. Uncertainty in the predictions, uncertainty in your estimation, right? Understanding that what exactly are the upper bounds and the lower bounds to that, because those are very important aspects in your policy decision, play into your policy decision, right? So how do you make a policy decision in the presence of uncertainty, right? This is our central theme here, right? But we will be stepping back a little. Right, it will be the material that I'll present is a little more sort of, in some sense, it's a little easier, right, than the situations that Udit was talking about. He was talking about really state-of-the-art models and trying to characterize uncertainty there. What we'll see here is the more introductory material for hypothesis testing, right? And basically, the idea is that look, here's the question: that given that you have made some estimation, right? How sure are you about this estimation, right? And this is important because you might need to make certain decisions based on this estimation, right? For instance, a common thing that you'll need to do when you write papers, once you start writing papers, will be that you need to be able to show that how are you performing against baselines, right? Certain existing baselines, right? So you will draw some curves. Right, you will draw precision recall curves of all of that, and or precision recall numbers. You will show that, okay, look, we are more than the baseline, right? But inevitably, the question there will be that, look, what does it mean, right? Because your training set is random, right? There are, I mean, the test set is random, right? So therefore, the performance itself is a random value, right? So if you get a difference, I mean, even if you are able to show, right, that your precision is 99%, whereas your baseline's precision was 96%. So there's 3% gap. How do I know that that is significant? Right? How can you show that that is actually meaningful, or is that if you do it 100 times, maybe one of these times it came out to be that, and you reported that, right? So you have to know, you have to report what is one of the significance value of your finding, right? And what does it really mean, and how do you calculate that? This is what we'll try to see today. There's already some chat. Attendees, okay, thank you. Yes, yeah, it will be nice if attendees turn on your cameras so that I can get to see you too. But before I start that, right, there's a very fundamental thing that I'll sort of cover before that, because that is the foundation of hypothesis testing, and this is called the central limit theorem. Yeah, how many of you have seen the central limit theorem? 2, no, not everybody. Very much, very good. 3. Okay. So let's see. Okay. So even before that, there's a funny puzzle. Okay, and this puzzle I found from this book by Daniel Kahneman and Amos Tversky. I don't know if I'm pronouncing it right. Who knows who Daniel Kahneman is? Huh? They both won a Nobel Prize. They both won a Nobel Prize. Yeah, and yes, in the behavioral economics, behavioral statistics. Okay, so this is the puzzle from their book. Okay, so let's say that I mean, Rahul is a random sample out of the Indian population, right? You have just picked up Rahul and you have just met him, and you're told that he's very introspective and likes to read books. This is the only piece of information that you're given about him. Just that, right? You have no other information about Rahul, right? And you're told that you have to place a bet on whether Rahul is a farmer or a librarian? Who would bet for, let's have a raise of hand for farmer, let's have a raise of hand for librarian. What would you bet? Any thoughts? Librarian? Unanimous? Why is that? Reads books and introspective. Yes. Should I go up 1,000 rupees, 10,000 rupees, 50,000 rupees? Okay. See, this is exactly what Kahneman and Tversky try to point out. When I say that this is a puzzle from Book of Two Nobel Laureates, it says that it's actually pointing out something intrinsic in our mindset. What he's pointing out is that we garble up what conditional means. Okay. So here are the 4 numbers that you need to think about, that you really needed to think about. We needed to think about the probability librarian given that they like books versus the probability of likes books given a librarian. Right? You understand the difference between the two. One of them, so you're given the information that this person is a librarian, and then you are saying that what is the probability that they likes books? That is the number you have in your mind. That number is high. Right? That probability is high. What I told you, what I asked you was to judge between these 2 probabilities. That given that they likes books, what is the probability that this person is a librarian versus this person is a farmer? This is what you placed your bet on. On the first pair, probability of a librarian given likes books versus probability of a farmer given likes books. Right? Whereas in your mind, when you did this bet, you looked at the second pair. What you thought in your mind when you also confidently place the bets was the fact that if you're conditioning on the fact that this person is a librarian, what is the probability that they likes books? Versus if I'm conditioning on the fact that they're a farmer, what is the probability that they like books, right? So we clearly need the first one, right? Why are they different? I can give you a formula, but here is a picture. I find this much more illustrative. Think of every circle and triangle as one of the possible members of this population. The circles are farmers, triangles are librarians, red circle is farmer and likes books, green circle is farmer and doesn't like books, red triangle is librarian and likes books, green triangle is librarian and doesn't like books. Okay. See. Now, think about what is happening. If you focus on the triangles, basically you're conditioning on the fact that this is a librarian. Then the fraction of red is more than the fraction of green. That larger fraction librarians likes books, right? Versus if I focus on the red ones, if I focus on the circles, the fraction of red in the circles is more than the fraction of red in the triangles. However, just the number of farmers, assuming it's a normal country, number of farmers is way more than the number of librarians that we have, presumably. I don't know, I'm just throwing out a statistic. And therefore, right, even if we're given the fact that this person likes books, the probability that they're a farmer is much higher than the probability that they're a librarian. Because when I say that I like books, then you have to focus only on the red triangles and the red circles. Then you have to see that out of the set of red triangles and circles, what fraction is circle versus what fraction is triangle, whether they're a farmer or whether they're a librarian, right? And there clearly the farmer wins, right? So when you're doing data analysis, be very careful to keep this in mind. What is the conditional that I really am looking for, right? And this will come in, for instance, probability that COVID positive given the PCR test versus probability of the PCR test given COVID positive, right? These will be very important numbers to make decisions on, right? And the same confusions happen there. Okay, but now let us go to something. Let's see this short video. Okay, so there's this tool called the Galton board, right? And okay, so now we turn it. So we think of it as sand, right? And we turn it back. it goes through these obstructions and it hits this curve. You get this curve. You do it again. You keep on doing it. Each time you get this curve. So okay, now before asking you why, let me explain to you what the board has. It has in these areas in the above, it has small nails basically. And once each ball falls, it hits this nail, and then it either goes, when it hits the nail, it either goes left or it goes right. Right, and then possibly hits another nail, and then it keeps on going. And the funny thing is that while you cannot possibly say anything about any individual ball, if you keep on doing this experiment, you always get this curve. What is happening? So some, I don't know, some Sadhu Baba here who's sort of doing this. Okay. So in a short, yeah. Here.
There are multiples of routes
that sort of plays a little bit of a role, but the basic idea of having the bottleneck is to say that all balls start with the same initial condition. I mean, you're right that if I spread out the balls, if I had many different holes at the top and spread out the balls, then of course it would not be like this, because the initial starting condition of the balls is different, right? But beyond that, I mean, why this shape, exact shape? That is the question that we'll try to see. And believe it or not, this in one video is what we'll be teaching about central limit theorem. This is central limit theorem, right? We'll come back to this video, and while I'll introduce random variables and sum of random variables, variance of random variables, I'll need you to come back to this video and say that what is the random variable here? How can I really apply central limit theorem in this picture, in this video, and say that look, I mean, given that I have studied central limit theorem, condition on that, this video is obvious. But let's see that. Okay, so yeah. Sorry. What happens then? What do you think happens then? That's a good question. That suppose the focal point is not at the center, but in one of the corners. What do you think will happen? So the center of the curve will shift to that corner. And of course, there will be other nasty boundary conditions that play in, because it will reflect out here because it is kind of bounded. The tail cannot extend beyond this boundary. So there will be a pile up here and so on, right? Presumably, basically then, you're taking this part of the distribution. Let's say that the boundary was here. All these balls would now bunch up to, in the bucket that's near the end. Right? That's some other boundary conditions playing a role. But let's see. Let us try to see why this could happen, right? And how does it relate to hypothesis testing? Okay. So of course, just to remind you, I know all of you know this. The Gaussian distribution or the normal distribution is what we'll be interested in here. And of course, it's a continuous value distribution, and we typically denote it as x follows n mu sigma. N stands for normal. Mu is the mean of the distribution. Sigma is the standard deviation of the distribution, right? And anybody wants to tell me the PDF? Okay. Okay. And again, I won't bother you. I mean, given that you're having an extensive course in data science, I won't bother you asking with these questions, right? The expectation is given by mu and the variance is given by sigma square. And these two quantities completely characterize the distribution. Just the mean and the variance completely characterizes the distribution. That is not the case with most distributions. Does anybody know this? That suppose you have a variable x1 that follows a normal distribution with mean mu1 and variance sigma 1 square. And another variable x2 that follows another normal distribution with mean mu2 and variance sigma 2 square. right? Suppose I have two numbers, A and B, and I use them to combine x1 and x2. So it is x equal to A times x1 plus B times x2. What is the distribution of x?
Will be normal again.
It will be normal with what?
A mu1 plus A1 mu1 plus A2 mu2 mean.
And
Not sure about the standard deviation. I've forgotten.
see, you don't need to mark this up. I mean, I'll sort of, so there are three things here, and two of them are obvious, one of them is a non-obvious statement. So one is that what is the mean of x, expectation of x? By linearity of expectations, it's easy to see that that is there. Okay, and I also cheated, and I want somebody to catch me when to catch me on this. The second question, the second important fact was that what is the variance of x1 and x2? Perfect. I did not tell you that that they should have been independent. In fact, if they're not independent, then even the variance statement is not true, right? I should have mentioned that they're independent, and if they're independent, then of course that the variance of x1, variance of x, is given by a squared times the variance of x1 plus b squared times the variance of x2, right? And we plug in the variances and we get the variance of x. So these two facts are not that interesting. They hold for any kind of variables. What is interesting is the fact that it actually follows a normal distribution with these quantities. That is the strange part. Why does it have to be normal, right? Why is it, I mean, of all things, there are how, I mean, does it happen for Bernoulli's? If I have one Bernoulli x1, another Bernoulli x2, and I add them up, do I get a Bernoulli? What is one line answer to the justification of the no?
You'll get a binomial.
If you add up two Bernoulli random variables, you get a Bernoulli random variable. And the answer given was no, a feeble no. I'm just asking that, just convince me in 10 seconds that your no is actually correct. So the question is x equal to x1 plus x2, but x1 is not but x1 is a Bernoulli, x2 is a Bernoulli. Bernoulli means 0, 1, let's say, right? And no.
Support itself changes.
It's a
Support changes because
exactly that's what I was looking for. The support of x changes. The support of x is now three values instead of 2. Therefore, it cannot be a Bernoulli. Forget everything else. That's a very clever way of looking at it. Okay, thank you. Okay. So now, so this is the important part. There are few other distributions that follow this property. We will not go into those. You will likely not have met them. But again, and they're very important once you go a little, once you study a little bit of statistics, but we will not go out here. Normal is the one among, I mean, the one that we sort of use the most, that combining two normal distributions, adding them up gives you a normal distribution. Okay, now let's see. It turns out that normal distributions are ubiquitous, right? And here are very, very strange numbers, right? For instance, this is the average number of goals that some person, I don't know, I'm not really a sports person, Alex Ovechkin scored in 82 games in his team, right? The average number of goals has been plotted out here. Well, look at this. It looks like a bell curve, right? Look at the presidential elections and the statistics, average monthly returns after presidential elections. You plot this, follows the bell curve, right? Look at average heights of English male criminals. I don't know, there are probably not enough female criminals. And that follows a bell curve, right? This is called a bell curve, right? And there are, I mean, lots and lots of these examples that you see that follows this bell curve. Why exactly is that? Right? Why does it have to be the same curve? I mean, whether it's cows producing milk or whether it's a summer temperature, there's no, I mean, possible reason on earth, right? Why would it have to be the case? Yeah.
there are multiple probabilities.
So that's a good point. That's a very good intuition. That's a very good intuition. Excellent. So the answer has been that look, there are many ways of reaching the center in some sense, what you're saying. But there's only one set of random events that will take you towards the fringe. Right. So therefore, the set of, if you look at the possible set of random events that take you towards the center versus the set of positive, that set of random events is more in number than the set of random events that take you towards the fringe. That's a very nice intuition. That's very nice. And in fact, that is what is formalized in order to show that this is exactly the bell curve. But the point I'm trying to stress is that not just the fact that it's high at the center and low at the at the end. It follows exactly this shape, right? And that is also the surprising part. But again, the justification comes from formalizing the argument that you mentioned. Okay, sorry. Press too much. Okay. Okay, so, and this is what is given by the central limit theorem, which is a very rich history. So before I give you the formal theorem, because the formal theorem is going to be, there's going to be some random variables and blah, 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 all of that. Let me just tell you what it is about, right? So that in plain English, you understand. See, this is what you should always try. Somebody writes a complicated mathematical formula in English, you need to understand what it's saying. Okay. Basically, it's saying that suppose you're trying to estimate some parameter X. Right? And you're trying to estimate that by sampling out of the universe of all possible values of X. So you sample and then you collect multiple samples and then you do the average and then that gives you an estimate of X of the real parameter X. This X can be, let's say, the average income in the population, right? So you're sampling and then you're calculating the average and then you're sort of looking at that average value out of your sample. Right? This is called the sample mean, right? So central limit theorem tells you that once you collect a sample, once you calculate the sample average, what is the distribution of the sample average? Okay? So we are not saying about the distribution of X in the population, right? Yes, we are talking about the distribution of the sample mean under multiple samples. That if you take sample number 1, calculate the mean number 1, sample number 2, take the mean number 2, sample number 1 million, take the mean number 1 million. What is the distribution of the sample mean 1, sample mean 2, sample mean 1 million? That's what it talks about. And that is an important quantity. First of all, right? It says that the spread of the sample mean will be less than the, let's take the point number 2. I should have put that first. Spread of the sample mean will depend on the spread of X, right? Because that is intuitive, right? Because if X is spread very, very widely, right? Or rather, think the other way around. If everybody in the population has the same X, then the spread of X is 0, right? When intuitively I've written spread, think variance when we're formalizing it. If everybody in the population has the same value, then the spread of X is 0, but then any sample you take will also have spread 0. All of them will have the same value. The other way is also true. Right? If everybody in the population has completely different values, right, and the spread is very high from 1 to, let's say, 100 million, then any sample you take, the spread will also be quite high. Rather, the variance will also be quite high. So number 2 is intuitive, but we will get there. Spread of sample mean will depend on the spread of X. Number 1, the spread of sample mean will be less than the spread of X, right? And here also, it's little less intuitive than number 2, but not very hard. Because what are you doing? When you're taking, this is really the sample mean, right? So it's like saying that I'm taking 50 people calculating the average, right? Average income. Just by the fact that I'm calculating the average, of course, that random variable that I get, the average, will be less concentrated, will be less spread out than the entire distribution, right? Because I'm taking the average. So therefore, number 1 is okay. After 2 minutes of thinking, it's possible. Number 3 is also very intuitive. That if I increase the size of the sample, the spread of the sample mean will decrease, right? And we know that that is always the case. That if you calculate, if you're taking a larger sample, the variance of the mean will decrease. Right? Okay, this is not that hard to get. Number 4, this is the most crucial intuition in the central limit theorem. the distribution of the sample mean. The distribution of the sample mean will be completely independent of the original distribution of X. Okay? So it does not matter how weirdly X is distributed in the population, right? And we'll see some examples. If you take multiple samples, right, and take the distribution of the sample mean, that distribution is completely independent of the original distribution of X. Right? And this is what helps us do a lot of statistics, basically the entire field of hypothesis testing, and can be characterized accurately. Well, this is under the assumption that you have taken a lot of samples, right? If you do this lot of samples, so this is in reality in theorem. I mean, actually, here the reality is better than theory, right? In theory, this is true only when you take a huge number of samples. Technically an infinite number of samples, asymptotics. In practice, this happens even if you have taken like 50 samples, 100 samples, even then it's enough. Okay. So I mean, how do we and what is this characterized accurately? How do I characterize that? No surprise, because it started with the bell curve. It will be the bell curve. It will be the normal distribution. The distribution of the sample mean will always be the normal distribution. Okay. Now, a little bit of formalism. So X is a parameter with mean mu and variance sigma square. So again, think of it this way. This method is called, I mean, I don't know. I saw this in some video of Feynman, called Feynman's method, right? When you see some things like this, right? Think of nailed down to a concrete particular sort of instance, right? When I say that X is a parameter, pick in your mind a favorite parameter that you want to estimate from Indian population. Think about it. Right? It could be the age, could be the income, could be the IQ, whatever. Right? And X is that parameter. That has a population mean mu and a variance sigma square. So this is the true population mean. If you could sort of look at all the entire Indian population and calculate that X for each of them individually, right? You would get the mean mu, you would get the variance sigma square. But of course, who does that? We don't know how to do that. I mean, as in, it's very expensive. What we do are we take samples from X, from the samples for X from the population. What does that mean? We pick up a random person and we ask them the X. We pick up another random person, we ask them the X. We get the values X1, X2, Xn. Then I calculate Xn bar. I'm writing N out here because it's an average of N things. I'm writing the bar because it's the average. And Xn bar is X1 plus X2 plus Xn divided by N, right? So it's a sample average, sample mean. So again, as you have seen, Xn bar is also a random variable. Right? Because it depends on which X1, X2, Xn you choose, right? I mean, do you in this room, if you choose me and then, sorry, Vinita, maybe you get a low IQ if you choose any, no, I'm sorry, you get a much higher IQ average. Okay, but then this Xn bar will be our quantity of interest. Okay, and we'll try to see that can we characterize the distribution of this Xn bar. Again, coming back to the examples that we were trying to say that, look, it's easy to say that the mean of Xn bar is actually mu, right? Because you take the expectation of Xn bar is equal to, just by linearity of expectation, the expectation of X1 plus expectation of X2 plus expectation of Xn divided by N. Now, each expectation of X1 is mu, expectation of X2 is mu, expectation of Xn is mu. So the numerator becomes N times mu and the denominator is N. Right, so expectation of Xn bar is mu, not a surprise. What is the variance of Xn bar? Anybody? Yes, please. Sigma squared by N. And how did you get that? The process is more important. Okay. So it is 1 over N square times the variance of X1 plus X2 plus Xn, right? The 1 over N factor comes out by taking the square because it's a variance, and then it is variance of X1 plus X2 plus Xn. Now, if we have said that these are IID, so therefore this quantity is 1 over N square, summation I, variance of Xi. Variance of independent random variables is the sum of the variances. 1 over N square, and in each of them you get N sigma square. Okay? And therefore we get Muskan's theorem, which is sigma square by N. Let us call it that. Okay, this is the variance of Xn bar. Okay, so until this point is easy. See, now you have already obtained couple of the results that we had seen in the sort of intuition of central limit theorem. The variance of x, the mean of xn bar depends on mu, which is population mean. Variance of xn bar depends on sigma square. So sigma square is high, the variance of xn bar will be high. Variance of xn bar decreases with n, because if the sample size increases, the variance of xn bar will decrease. These were two of the three intuitions, two of the four intuitions that we were kind of saying, right? And I mean, actually three of the four intuitions. The variance of xn bar is less than the variance of x, right? Because sigma square by n is less than sigma square. Okay. The important part is the fourth intuition, which does not come out of here, which is saying that it sort of will follow a normal distribution, right? So just to visualize what I was saying, right? Again, this is not nothing new, just that formula I have put it in pictures. Suppose the left hand side is the distribution of x. It's a weird distribution, bimodal distribution. Okay. And let's say x1, x2, xn are sort of some. I mean, that has a mean mu and a variance and a standard deviation sigma. That is a population distribution. I don't know what it is. What do? I take multiple samples of size n. So x bar, again I do another sample and calculate x bar. Again I do another sample, calculate x bar, and I'm plotting these x bars. I'm not plotting the samples. I'm plotting the sample averages. The cumulative distribution, the PDF of that. And that distribution I can characterize exactly irrespective of what the left hand side is. The mean of that will be mu, as we just saw. The standard deviation of that will be sigma by square root n, as we just saw. Importantly, that distribution will be exactly a Gaussian. Okay, that's what we will see in the formalization. This is a picture demonstration of the picture of the central limit theorem. Okay. I mean, here is the, again, we'll sort of do it very concretely. If you're getting bored, let me know. I'll sort of will speed up. Here is an experiment. Toss a coin 50 times. Count the number of heads, right? In that 50 times. Call it H50. Divide by 50. Does not matter. It's just a scaling, right? You do the above experiment multiple times. So this is H150, right? Is one set of experiment where you have tossed the coin 50 times and you have calculated the number of heads. H250 is another set of experiments. HN50 is another set of 50 coin tosses. Now we create a histogram for HI50, right? And these are the two here. These are the two histograms. Here is a histogram where we have done 200 experiments, right? And calculated 200. So capital N is 200, right? In each experiment, you're still doing 50 tosses, but you're doing 200 such experiments, and you draw the histogram of these numbers. Here is the plot that you get. Again, right? 200 is not too large. Here is the plot that you get when capital N is 10,000. It approaches the bell curve much more accurately, right? So this is very simple illustration that you could do yourself. I mean, what happens when P changes? Supposing now, instead of having a single coin, you have three different coins. You have one coin in which the probability of a head for each toss is 0.5. Another coin in which the probability of head for each toss is 0.7. Another one in which the probability of it is 0.5, and you do smaller number of experiments. The shape of the curve will be the same. Just the center of the curve will change. The standard deviation of the curve will be the same. Will change. Those two will depend on these parameters, but the shape of the curve will be the same, modulo these parameters. Yes. Always equal to 1. It's a probability distribution. Yeah. So in some sense, what you're saying is that if you're doing 10,000, the area under this histograms is 10,000. I have normalized that by 10,000 in order to do that. Okay, the central limit theorem. This is now the actual sort of jargon. We are saying that x1, x2, xn are IID with mean mu and variance sigma square, right? This is the original version. Well, not the original. The original is a little buggy. This is what is known as the Lindeberg-Levy central limit theorem. So a lot of history will come up, right? And it says that there has to be certain conditions, right? Take any sequence of IID random variables, and the only conditions I put is that the expectation is bounded and it's mu, right? And the variance is bounded. This is a very important condition. It turns out variance is a finite quantity, and it's a quantity which is sigma square. Let's say, let me denote by that. So all of these are all of these is the same IID random variables, okay, identically distributed with the mean mu and the variance sigma square. So identical is important. Now I let n approach infinity. Then, and I look at this random variable, right? Sn, which is equal to summation xi by n, right? I look at Sn, which is equal to summation xi by n, right? And I look at square. So the expectation of Sn will be mu. So this is Sn. I should write this as Sn. Okay. And I look at this quantity, square root n Sn minus mu, right? It turns out that this quantity, see, this square root n is just to handle the scaling out here. So don't worry too much about that. But this quantity, which is a random variable, will converge to a normal distribution, Gaussian distribution. Its mean will be 0 because Sn has expectation mu, therefore Sn minus mu is expectation 0. So the expectation of this quantity will be exactly 0. Variance of this quantity you can also sort of figure out will be exactly sigma squared, and this will converge in distribution. That's what this D sort of says, that this converges in distribution. This random variable converges in distribution to the Gaussian distribution. What it means is that you do multiple instances of this random variable and draw the PDF, you get the Gaussian distribution. Going very slow. Okay, so just a little bit of history, because in maths, in sort of maths data science, I feel like we don't do enough history. We don't understand where everything came from. Nothing comes all packaged and canned as we see. So everything goes through a lot of varieties. So the first version came from, the empirical observation came from this person called, mathematician called, I don't know, it's a French name, Quetelet, I'll just say, right? And he got it by plotting the chest circumference of Belgian soldiers. That was a quantity of interest to find out the average man, right? And he observed that there's a particular distribution that we are approaching, right? 1812, Laplace had already observed much before this empirical observation, and there was no communication there at that. The communication was very slow at that point. And he talks about the formula for large numbers, right? And here he sort of said one of the delicate open problems was the comet observation angles. He talked about the mistakes in the instruments, and therefore the variation in the observation angles that come from there. And he talked about their distribution. Pretty amazing, right? So very, very empirical rules. And he kind of sort of mentioned that we should try to characterize this distribution that comes solely from this instrumental errors, right? He did not quite do it. He had the entire fabric for the central limit theorem, because he defined random variables for the first time, right? He was talking about their sums. He's talking about what does this sum approach, the distribution of their sum, and he used that to predict, right, the angles of comet orbits. But he never really sort of talked about that this is a particular theorem. He never really defined that. After that, a lot of mathematicians have worked on it, very, very famous mathematicians, and they all kind of refined it in the form that we have it today. Right? This is what we have. So again, just to be very concrete, here is an example. Here is suppose you have a particular dice that has 6 heads, 1, 2, 3, 4, 5, 6. Head number 2 and head number 5, they have 0 probability of turning up, right? Head number 1 and 6 have same high probability of turning up. 3 and 4 have slightly higher probability. And I did a bunch of, I have not given in the code, but I did a bunch of experiments. So suppose I roll it 4 times, n equal to 4. So 4 is my sample size. I get 1, 1, 3, 6. This is mu1, the average of this. I roll it again 4 times, mu2. This is average. See, I cannot get 2 or 5 because those probabilities are 0. So this is mu2. See, this quantity is not at all random. It's bimodal. Sorry, this quantity is not at all normal. It's bimodal, so it cannot be normal. But here I'm doing 4 tosses each time and calculating the average, right? Then I look at the distribution of these average quantities, the mu1s, right? And that is what we are saying will be a Gaussian distribution, and the mean will be given by the mean out here. Once you calculate these probabilities and the heights of these probabilities, multiply them, that will be the mu and the corresponding variance. But the shape will be that. Okay. So this is a central limit theorem, and we'll utilize that very soon. Before that, another twist to the tale. Suppose I ask you to plot the income wealth or /wealth, whatever you call it. Income and wealth are slightly different. Yes, but let's just say choose any one of them. Let's just see the total wealth, right? Let's say that you try to plot on the x-axis is the total wealth, and on the y-axis is the fraction of world's population, right? Will that be a bell curve?
Probably.
Yes. Hmm. 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 Okay. Hmm. What do you mean a skewed bell curve? Hmm. True. Hmm. 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 So let us, I mean, so very simply. So first of all, it cannot go negative. Let's say that there's no negative wealth. And secondly, so then large fraction of the population is is at total wealth fairly small, right? And then it's clearly going down, right? But what I'm asking is that, is it going down as fast as what I'm also asking, is it going down as fast as the normal distribution would? Right? So the normal distribution goes like exp of minus x square. Right? That's how it goes down. Right? Do you think the wealth distribution, right, is going down in this plot is going down as fast as that? Yes, no? So for instance, right, what this says is that look, if you take, I mean, again, this the confidence intervals of the normal, right? If you take people who are whose standard deviation, who are, let's say, 10 standard deviations away from the mean, the probability of that, right, is like e to the power minus 100. 10 standard deviations from the mean would be, because of the x minus b by sigma square, would be exp of minus 10 square, which is exp of minus 100. Right? You have a sense of how large e to the power minus 100 is. Again, my favorite, e to the power minus 100 is almost as big or possibly bigger than the number of atoms in the universe. So there would be nobody who's 10 standard deviations away from the mean. But we do have a significant middle class. We have a significant number of, well, some billionaires and some not quite billionaires, but that number is not insignificant. So basically, this goes down much slowly than what the bell curve would. Right? The bell curve might actually go down, as in this function might go down much faster. This go down much slowly. So it does not follow a bell curve. You might say that, oh, this is modern day and age. Right? This is the US income distribution. You see that this is not really a bell curve because the tail is, I mean, one important part is that it is kind of truncated, right? Because the negative is not there, right? On the x-axis is the income less than certain quantity, and the y-axis is the number of people. But you also observe that the tail looks a lot fatter than the bell curve, right? And so it's a little strange. Why is that? More of history. This is basically a characterization of the wealth distribution in an ancient Egyptian society. So how did they measure it? They sort of took the floor areas of the houses, right, and used that as a proxy for wealth. Yes. Somebody with higher wealth has a larger house, presumably, and that also does not look quite like a bell curve. So what is all the central limit theorem we're talking about, right? And this looks a lot fatter, right, than the bell curve. So in fact, one way of understanding these curves, how different them are, is by plotting against what is known as a log-log plot. See, in this axis and in this axis, right, we are plotting, I mean, this is linear linear in the this is house area, exactly linear in that. This is the number of houses. Supposing on the x-axis I took log of this quantity, log of x. On the y-axis I took log of y. Okay, so what would a bell curve look like in there? If I plotted, if y equal to exp of minus x squared, what would a log of y versus log of x look like? It would be log of y would be equal to minus x squared, right? I mean, log of y is e to the power minus x squared. So therefore, if I plot it, right, it would, how would it look like? It would definitely not be a straight line, because log of x Let me show you the plot. But okay, but the interesting thing is that I mean, if you plot this in an axis where the y-axis is x-axis is log and the y-axis is log, you basically get the data which is a straight line, right? What does it mean? What it means is that you're saying that log of y is some m minus a times log of x, because that's the equation of the straight line out here. I mean, let me write this to be a minus m times, m is the slope, because a is the intercept on the y-axis and m is the slope. Log y equal to a minus m times log of x. What does it say about y equal to? If this line is log of y is equal to a minus m times log of x, what does it say about the relation of y versus x? Y equal to exp of this quantity. So exp of this quantity is e to the power a divided by e to the power m log x. What is e to the power m log x? I'm hearing some noises. X power m. So this curve, right, if the data follows like this, it would say that look, see, this is very different from saying that y equal to e to the power minus x squared, right? We are saying that y equal to e to the power, y equal to some constant times x power m, basically decays polynomially, not like e to the power minus x squared, and that would be a very different distributions. Okay, so it turns out that this is also a very common phenomena, and this is called the power law distribution, or the sort of long tail phenomena, right? If you look up the Wikipedia entry of long tail, you will see that at this point, right, I mean, it is almost as ubiquitous as the central limit theorem, right? For instance, I mean, yeah, this is the plot. Here I have plotted k versus I've plotted x-axis and y-axis both in logs, and the green curve, right, is the normal distribution curve. This is how the normal distribution would look like, right? In the green curve, it's basically a normal distribution. I mean, it's really a Poisson, which is close to normal. That's how that would look like. This is what the straight line looks like in the straight line in the wealth distribution that we talked about. This is called a scale-free network, right? So while I sort of said so many great things about the central limit theorem, right, there are equally sort of problematic places where you will see that it cannot really apply the central limit theorem, right? It does not really follow the same kind of distribution, right? And for a while, for like the 90s and also in the 2000s, this was a very common area of research, and this is something that you need to sort of take care about, right? For instance, if you see the number of friends that a person has on Facebook, if you plot the distribution, number of so for each person, look at the number of friends that they have, and then you plot the PDF of x-axis is the number of I mean, y-axis is the x-axis is the number of friends that a person has. Y-axis is how many people have that many friends. How many people have 10 friends? How many people have 20 friends? How many people have 10,000 friends? That's the y-axis. That is not a normal distribution. That will not be normal distribution, right? And there are very interesting models that come in trying to explain that why does this happen, right? The entire 1800s and 1900s have gone in trying to figure out why central limit theorem, the proof of the central limit theorem, why that is so ubiquitous. And then people started sort of discovering that it's not so ubiquitous, and there are natural explanations of why will it not happen. But we will not go into that. What we will do is that we will sort of rely on the central limit theorem in order to do our hypothesis testing. So let us start with that. Any questions until now? Let me just see. Yeah.
There is a question in the comment.
There's a question in the. So can Samir, please, can you speak out?
Yes, sir.
Yeah. Just any question, please speak out.
No, sir, nothing.
Oh, no question. Okay. Okay. So for now, we'll just imagine that the central limit theorem is what we believe in. I should tap here again. Okay, good. Okay, so now, and again, but you should read this book if you want to see, if you want to understand this long tail or the power tail. There's a very famous book by Chris Anderson who says that look, the phenomena that there is a long tail is actually a very important business model for let's say Amazon, right? What is the success story of Amazon against local stores? And you can characterize Amazon as being somebody with an infinite sort of store size, right? And with a good recommendation system, but because of the infinite store size, it is able to pick up on the long tail of very esoteric people's interests, which a local store cannot do because of its finite store size, right? And that's a very important business model that he sort of characterizes in this book. Okay, so let's come back to our main story, the hypothesis testing. Here is the broad goal, right? That suppose you want to say that whether a coin is fair. How can you do so, right? You want to answer more importantly, who cares about coin being fair? Well, you do. You want to answer the following question. That is the average income in state X more than average income in state Y? Very important political question. And while you could go and ask everybody in state X, that is too much of, that's just too much state expense spent there, right? So you have to take a survey. You take a survey and then try to answer this question. More importantly, right? In the COVID pandemic, for instance, how did we know that vaccines actually create an effect? Specifically, if we administer a particular drug, does it cause an effect, right? What does the FDA do in terms of testing before they release a particular drug, right? Because if it's just a sugar coating, right? If it's just a sort of pound of a pinch of sugar, that the FDA will not characterize as a drug, right? And how does it know that a particular drug does cause some change to the specific health parameters? And we'll see. More importantly, questions that we also look at here. So does anybody know of these gravitational waves? Yeah, gravity. The gravitation in the gravitational waves, there's a huge amount of noise. See, anything that you do in this building, you step loudly, and that will be a blip in this interferometer, right? So how do they filter out all these noises and be able to say that no, this is a significant blip versus this is not a significant blip, and that I can attribute to noise. This I cannot explain via noise. Right? How do they how do they answer the scientific questions? It all comes down to hypothesis testing. Okay. So some terminology again, as we were kind of referring, there will be a population, then there will be a sample, right? What we want to say is something about a population parameter, right? Population parameters are things we want to sort of make statements about, as we were saying, like in the state income. The population parameter is the average income of the entire state. We want to say something about that. We cannot access that. We can access the state, we can access the sample, and we can estimate the average income of the sample, right? And based on average incomes of the samples, the sample averages, are we able to say something about the population averages? And a hypothesis intuitively, while we will give a slightly formal definition, is a statement about the population parameter, right? While looking at only the sample values. Now, the terminology, some terminology, right? And okay, we'll come to that. Let's call theta to be the population parameter. It can stand for whatever. Theta will be the suppose theta is the probability that the coin will give a head. Right? So theta is not observed. And typically, the way we phrase the standard hypothesis testing is that we talk about two competing hypotheses. We talk about the null hypothesis, we talk about the alternate hypothesis, right? So you'll be the, I mean, and then there'll be the question of what is the null hypothesis, what is the alternate hypothesis? I mean, of course, something is true versus something is false, right? So let's see. I mean, there's a little bit of subtlety in what you can call the null hypothesis versus what you can call the alternate hypothesis. Okay. So, and the goal of hypothesis testing would be to see that which of these do I trust? Do I trust the null hypothesis or do I sort of trust the alternate hypothesis? In fact, it's a little bit more than that, right? We'll sort of see the subtlety there. The null hypothesis. So how do you choose a null hypothesis? What is a null hypothesis? So there are a couple of guidelines I will give in choosing a null hypothesis, and then we will think about some examples tomorrow, right? One of the guideline number one, the thumb rule one, is that the null hypothesis is typically one that measures the absence of an effect. Right? That is what you should choose as the null hypothesis. There's a very good reason for that. We'll talk about that when we talk about A/B testing later. Supposing we are kind of seeing whether a particular drug that was claimed to have an effect on blood pressure, right? We are trying to do hypothesis testing on that. We're trying to see that is that really the case, right? Then we choose the null hypothesis to be this statement that the drug has caused no effect on the blood pressure, right? That there is no effect. Right? The H1, the alternate hypothesis, sometimes denoted by HA, sometimes by H1, is that there was an effect, right? That there was a decrease in the blood pressure or something. Okay. So this is an intuitive sort of thumb rule. So the null hypothesis indicates absence of an effect. But what does it mean? There's a little bit formal, way of choosing a null hypothesis. Basically, we will see again examples. Null hypothesis should be such that under the null hypothesis, we should be able to say that what is the distribution of the test statistic. There'll be something of the test statistic, which is what we measure from the sample. The null hypothesis should be such that we can characterize that if the null hypothesis were true, just because of randomness, what is the variation in the statistic that we are measuring? I'll repeat. Null hypothesis should be such that I should be able to say that if the null hypothesis were true, conditioned on that, what is the variation in the test statistic just because of randomness? We should be able to characterize that accurately, because that is an important point. Either characterize that using mathematical formulas in specifically the CLT, or characterize it by plain simulating the data, right? Simulating it randomly, doing NumPy or random, you do a bunch of simulations and do this. We'll see a lot of examples. Suppose I want to do quality checks on items. Quality checks means that you are given a bunch of items. You are, let's say, Anand here has a factory of pencils, and he's saying that defective pencil is one which breaks easily. Okay, and he's saying that okay, in every, what is the fraction of pencils that you're producing that are defective? Okay, so the null hypothesis is theta is the fraction of defective items. So this is what I call as a statistic of interest, as a test statistic, right? That what is the fraction of defective items that we're producing? Theta 0 is some threshold. Okay, that he's saying that look, I'll accept this batch only if my theta is smaller than theta 0. Else I'll have to redesign the entire machinery. Okay. So now if you're trying to decide whether to call this a good batch, right? In that case, the null hypothesis should be to say that the theta is bigger than theta 0. Theta is bigger than theta 0, which is I'm taking the pessimistic view. That is a null hypothesis. Okay, that the fraction of defective items is bigger than my threshold, i.e. my batch is not a good batch. What we will say, and the alternate hypothesis will be the complement of that, what we will try to do using hypothesis testing, and this is the key thing, is that we'll always try to see is that whether we have overwhelming evidence to rule out the null hypothesis. We will always be trying to rule out the null hypothesis, and therefore we take the null hypothesis as something that is the pessimistic view, and only in case of overwhelming evidence we say that is not true, and the alternate hypothesis is true. If we don't get overwhelming evidence, we'll say that we have no way of saying that the null hypothesis is false. Right? Again, just to repeat, this is a slightly tricky thing, Because let's say that I mean, this is like, think of it as the following, right? What does the code do, right? In saying that, in sort of saying that whether somebody is guilty or not, right? See, the code, I mean, what does the law say? The law says that somebody is innocent until proven guilty. That in order to say that somebody is guilty, you have to have overwhelming evidence. If you don't have that, right, then I cannot pronounce that person guilty. It's not that they're innocent. I'm not pronouncing them innocent, that I cannot pronounce them guilty. That's what the law says, right? It's exactly that, right? Because I'm not saying, I mean, we will never be able to say that the null hypothesis, I mean, we'll be never be able to say that the null hypothesis is the state of the world. We'll just be able to say that, we typically just say that we cannot rule out the null hypothesis. Okay, so let's say that I mean, suppose we are saying that we have a coin toss, right? And so now this is another intuition in choosing the null hypothesis, right? And the parameter of interest is theta, right? And we say that the theta is the probability that that it comes up with a head, right? And the broad question that we're asking is that, is this fair? Is this fair, right? Now there are two possible null hypotheses here. There's a probability that theta equal to half. This is one null hypothesis. The other thing is that there's a probability that you said the theta not equal to half. This is a null hypothesis. Now, are both equally suitable as a null hypothesis? Can I choose this as a null hypothesis? Can I choose this as a null hypothesis? What do you think? Second one should be the null hypothesis. First one should be the null hypothesis. So this is a subtle question actually, because what did I say? I mean, another thing I said about the null hypothesis is that under the null hypothesis, right, we should be able to simulate we should be able to sort of get the distribution of the test statistic and say that what happens due to randomness if the null hypothesis is true. Now, if I choose this as the null hypothesis, theta not equal to half, it doesn't say much, because 0.500001 is also theta not equal to half. Theta equal to 0.9 also satisfies theta not equal to half, right? So so this null hypothesis does not give me enough information to tell me that what is the distribution of the test statistic under the null hypothesis. This is a very imprecise null hypothesis. So this is not the right null hypothesis here. The null hypothesis is here, is this one, right? The right null hypothesis. And then we'll be able to say that only if we say an overwhelming number of heads or tails, we have an overwhelming evidence that the coin is not fair. That is, we reject the null hypothesis, else we go with the assumption that the coin is fair. Okay, so we'll see why we are doing this. Some applications when we do the A/B testing. Again, fundamentally, it's about understanding what conclusions we can reliably draw, right? In the sense that, see, we'll never be 100% sure, right? So, so this is because there's always randomness. So it's by saying that what is my confidence interval and that I need to account for just because of randomness, and understanding the trade-off of the size of the interval and the confidence that I have, right, that we are drawing the conclusion about just based on a sample. So the sample size will come in, the CLT will come in, all of that. And of course, there's a lot of caveats. Again, we'll see examples of why hypothesis testing is not necessarily the right thing to do always, right? There's lots of things called p-value hacking and all of that. And even interpretation of p-values, I mean, is problematic sometimes. But I mean, in order to see where it is problematic, you first have to understand the setup, right? Before you say that this is where you should not use it. So, okay. So let me just do this slide and then we'll retire, then we'll talk about it tomorrow. Okay. So the basic framework will be the following. Okay. There'll be a test statistic, which is basically a statistic that summarizes the data. I mean, you might not have the term statistic, like the mean, the median, right? The standard deviation. These are all statistic of the data. Okay, so so there'll be a test statistic, right? And then the goal of the hypothesis testing is always the following, very, very limited, is to see that whether we can reject the null hypothesis. Am I in a state, right, where I can, where the value of my test statistic is such that I can reject the null hypothesis, or I'm not able to say that I reject the null hypothesis, right? So what do we start by? We start by presuming that the data actually follows the null hypothesis. This is a presumption. This is under this assumption, under this presumption. Now I see that, okay, if the data follows the null hypothesis, what will be the distribution of the test statistic? And since if the coin is fair, what will be the distribution of the number of heads, right? And then I see, and then I do, and see, this part is only simulation, either simulation or mathematics, line number 1. The second, and then I go to the data, and then I actually do the coin toss. And then I see that out of 100 tosses, how many do I get? Right? And there, for instance, I get 99 heads. Then I said that, look, if the null hypothesis were true, if the coin were actually fair, the probability of getting 99 heads out of 100 is like 0.00001. Therefore, with confidence 1 minus 0.00001, I can say that I reject the null hypothesis. That's what we say, right? In this very simple example, this will become more complicated in other examples. So again, the first is that under the null hypothesis, once you assume the null hypothesis, you should be able to say that what is the distribution of the test statistic, right? And then you do the experiment, right? And using the experiment, which is basically the sampling, right? And then you figure out the value of the actual value of the test statistic, and then you see that, is this the test statistic that I observe? How likely is that under the null hypothesis assumption? So just to step ahead, that is what gives you the p-value of the test, right? We'll sort of define that formally. Okay, so let me okay, I'll start with genetics tomorrow. Let me again stop out here. Let's see that people look a little tired. So we'll sort of follow Gregorian priest, Gregor Mendel. Who knows? Okay, I've already written out. He's the father of genetics, of course. And so he did amazing experiments that we can look at it from this hypothesis testing point of view. We'll sort of see that tomorrow when we discuss. Any questions? Well, you will have to first decide a confidence threshold. You will have to say that, look, I mean, I mean, that is a p-value threshold, right? You will have to decide that, look, I will reject the null hypothesis if the observation that we are seeing is less than 5% likely or less than 1% likely. So that is completely qualitative. There's no argument behind that. Why people sort of say something to be significant if the p-value is less than 0.05? No good reason. Somebody picked it out of the hat, and then since then we've been following it. But once you pick the threshold, and then for that threshold you say that, okay, this is now, I mean, with this threshold I can reject the null hypothesis or I cannot reject the null hypothesis. The threshold choice is qualitative. Any questions? But very good question. Yeah. Very good question again. I mean, there is multiple hypothesis testing. That is a lot harder, because then there are, I mean, you're making the judgment between multiple hypotheses. Yes, there is multiple hypotheses. Yeah. So let's say you want to, I mean, let's say you have 3 different categories, and you want to say that I mean, I'm just coming up with an example, so this might not be a very good thing. And you want to say that, okay, yeah. So let's say that you want to classify countries as underdeveloped, developing, or developed, right? And for any one particular country, you want to take its sample and the sample income and want to categorize it in one of these. So that could be multiple hypotheses. Yeah. Very good point again. Are we assuming that the data is IID? we will almost always be assuming that the sample that we take is IID. The sample that we take from the population is not IID. Population is what it is. The sample that we take are IID samples. And in fact, this also leads to a number of very interesting questions, some of which Rishabh only hinted to, is that how do you do something like this if the data is actually something like Facebook? Facebook's peoples and their interactions are not IID. If your friend clicks on something, you are more likely to see it. What your friend does, it influences you. So being able to do hypothesis testing on non-IID data is a very important research question. Applies, it applies. Yeah, there are, I mean, people, for instance, in this, again, general non-IID data, I cannot say. In the case of the network bucket, there are ways that people have found out, I mean, have developed for network bucket testing. Sort of, I mean, those are much more complicated algorithms, but the simple tools don't apply. You'll have to sort of figure out things. For instance, you can sort of take things that are far away from one another. I mean, see, if the interaction is arbitrary, you cannot do anything. But if the interaction, for instance, you and let's say, I don't know, Kim Kardashian, what she does, how much effect does it have on you, or what you do, how much effect it has on her. Right? So I could take you two as basically independent of one another, right? So there are things like this that people do. Control group and yes. No. You don't provide it to any of them, actually. Yes. Yeah. So this is an IID sample. We start with an IID sample. However, this is a little, I mean, even here, there's a lot of, which is why vaccine trials took a long time. What do you mean by an IID sample, right? Because see, there are so many stratifications of society, right? And there are so many things that come into play in sort of, could potentially be a confounding factor in sort of your vaccine results, your age, your past history, right? Your sort of, the set of diseases you have suffered, the blood pressure that you have. How do you sort of, how large of a sample do you have to take that you say that this is actually representative sample across all of this? Across all of these categories? That is not an easy question to answer. For instance, I mean, here is a question that you could think about. Suppose I wanted to do hypothesis testing for, let's say that somebody says that I have personalized genetics-based personalized medicines. How do you do hypothesis testing for that? I don't know. I don't know if anybody has thought about that. Because by nature it is personalized, right? So what does it mean to have 2 IID samples? I don't know. I mean, and in fact, on the flip side, I don't know if I'm sort of hurting anybody's sentiments, that some of the arguments that goes behind saying that why that homeopaths have been saying that why hypothesis testing is not the right way of saying that homeopathy does not work. Because it says that it is so individualized to everybody that you cannot sort of use hypothesis testing or blind tests in order to judge homeopathy, right? Which is a questionable argument to me, but again, it depends on your belief. Okay, any other questions? Any questions from the online audience? Okay, thank you then. We'll see you at 2. At 2. Today I did not make a mistake.